Hello, my name is Erich Renko and I am the author of the paper The Robustness of the Edge Detection on Noisy Natural Images with HED and the PiDiNet networks. Now I would like to give you a presentation of this paper. Let's start. So first, the problem statement. The paper focuses on edge detection in natural images with RGB color channels. The relevance of the work is related to the widespread use of the procedure of edge detection on images as a pre-process in computer vision. For example, presented images demonstrate a processing frame from a car's autopilot system. The initial image is fed to pre-processing for edge detection. On the resulting edges, the system recognizes objects in the environment: cars, obstacles, road marks. In this case, the system has recognized the road marks and used it for navigation. But in invisibility conditions such as low light, bad weather, or noise, image details may be lost. Additionally, artifacts may appear leading to the loss or true edges or appearance of false edges. Under such conditions, the navigation system make mistakes. Literature review. In the literature, in view of robustness, the conventional edge detectors not using CNNs are divided into two groups. So it was proposed classifying edge detectors as differential and correlation methods. If the CNN have some gradient operators in the convolution course, we classifying it as a differential method. If the CNN includes conventional convolution course, we propose to define it as a correlation method. Here we presented a comparing table for proposed method. Here we have a concept of neuronal network, example of it, and advantages and disadvantages for all. The idea of the paper is to research the result of natural image edge detection by methods of this group in condition of varying noise level on the image. Next, materials and methods. To research the robustness of edge detection with HED at PiDiNet networks, the next technique is proposed. The stages of this technique are as follows. First one, CNN architecture selection. The literature review result is the selection of one or more CNN for edge detection procedure. Next, definition of noise type. The researcher needs to select the type of noise as well as the noise parameters to be investigated. At this stage, mathematical modeling of the noisy image is carried out. For example, on this slide we also present the noise of models that have researched in this paper. They are provided here. Next, third one step. CNN training and test set preparation. At this stage, the researcher has to decide on the test data sample. In this paper, the BSDS 500 test set is used for training and BSDS 300 is used for the image test set. Controlling image corruptions. According to the selected types of noise and intervals of the parameters, the images are officially noisy. 5 steps. CNN training. A previously selected neuronal network architecture is trained to detect edges on the selected test set. Here is provided the HED network architecture, which is used in this paper. Next, 6th step. Performance metric. Numerical metrics should be used to evaluate the resulting image edges. The method proposed to use precision, recall, F1 score, and form, based on the resulting edges and ground truth data from test set. Next, we have pixel-different convolution applied by PiDiNet network. PiDiNet is also used in this paper. 7th step of this technique is edge detection of noisy images. A trained neuronal network is used to edge detection of a set of noisy images with different type of noise and its parameter, which was set earlier by the researcher. And last one, analyzing the obtained result. After the edges detection procedure is completed, the researchers will be able to evaluate the effectiveness of particular neuronal network on images with previously selected types and noise parameter. As a result, a recommendation can be recreated to use a defined neuronal network architecture with relation to the type of noise on the image. Next, experiments. In order to confirm the developed method, an experiment was performed. First, the previously reported HED and PiDiNet neuronal networks trained on the BSDS500 dataset and used in this experiment. Next, the model of analyzed noise are chosen as follows: white Gaussian noise, impulse noise, and multiplicative speckle noise. Next, the BSDS300 test set images were put under controlled noise addition with the following parameters. Gaussian noise was corrupted from 1 to 45 with a parameter increment of 5. Next, impulse noise from 0.01 to 0.18 in steps of 0.02. And finally, the speckle noise from 0.01 to 0.3 with step of 0.05. The previously selected neuronal networks are used to detect edges on the noisy images. The detected edges are evaluated using the recall, precision, F1 score, and form metrics, and resulting metrics values are analyzed for further decision making. Results here. So the obtained during the experiment matrix values are presented in the form of graphs. These graphs demonstrate the dependence of metric value to the edges detection accuracy result on the level and type of noise on the image. From the graph, we can notice the trend as level of each type noise is rise, the accuracy of result of edge detection by PiDiNet is decrease, while HED shows better stability in every one case. Finally, conclusions. The obtained results are presented in the form of recommendation table for the choice of edge detection methods depending on the noise on the image. The results confirm previous conclusions that differential method of edge detection are better for low noise images, and correlation method shows better result on image with high noise parameter. So that's all. Thank you for your attention.